Lab 4, Oscillation. Introduction. The purpose of this lab was to model the motion of an oscillating mass at the end of a spring to calculate certain aspects of the system in question through symbolic algebra and the mass's path. The experiment observed with initial conditions of 0.402 kilograms mass oscillating on a spring of relaxed length 0.1265 meters with the spring constant K 6.87 newtons per meter at a stretch length of 0.7 meters. This system found y-axis oscillation period, which was 1.52 seconds, which is approximately the same period for the x-axis base period. Hooke's law, the energy principle, kinetic energy, and why we need them. The system in question, the mass is attached to the spring and it's in motion. Though the reason the system has constant energy or zero change in energy, therefore the kinetic energy of said mass in motion is equal to the changes in potential spring energy as well as gravitational potential energy, as this is a vertical spring setup. Of course, with observing motion in any sense and updating velocity, the position given net force, Newton's second law and its postulates are required. Symbolic algebra and given equations. In order to find relaxed length as well as the spring constant, symbolic algebra for the period in the y direction had to be used, thus allowing us to manipulate the variables to find these initial conditions. The period was found from tracker, and then putting that into the equation for period using the spring constant K as well as M, then you could find that spring constant K, and then using that you could plug that into the spring force equation to then find that relaxed length, which is how we got these initial conditions in the first place. System and surroundings. For the observed system, the system itself under study is the mass oscillating attached to the spring with components of potential energy from spring force and gravitational force. The surroundings are everything else in the environment around it. Tracker video and data. As you can see at the beginning of the video, the mass actually doesn't follow time linearly and actually teleports, so that's going to come up to some error solutions for the lab. Computational model components, part 1. In my computational model, I initialized my conditions for the system in known variables. I then modeled the equations for L from Hooke's law, kinetic energy, gravitational potential energy, and spring potential energy, as well as modeled the full energy principle with their sum. For part 2, the model then sets initial values for kinetic, gravitational, spring, and potential energy to find change in which after they iterate through the loop. It then models the equations for force of gravity and spring force, as well as the postulates of Newton's second law of motion, the velocity and position update formulas. Finally, after this iteration, the change in each is calculated and the loop runs, again making our curve data over time t. Sources of error. The video initially had a lag where the mass observed teleports to a leftward coordinate without time passing in the correct interval. Once correcting this and putting the initial coordinate as the coordinate to the left value rather than in the middle teleported, the graph of the system energy is much more accurate with a total energy and change in total energy summed at 0, which fulfills the energy principle. The lab ultimately exempted the energy principle as the model with the empirical input displayed 0 change in total energy with the sum of the system's kinetic and spring energy, as there's no energy loss. Overall, the computational model was accurate for energy and slightly less accurate for position of the mass, likely due to human error of placing each tracking point in the tracking software. What if and what does it mean? For each system, is the energy principle satisfied? As stated before, the total change in energy was 0, therefore it does satisfy the energy principle as no energy was created nor lost. And then using the data you obtained in Tracker, made 2 separate estimates for oscillation periods. My X estimate was 1.66 seconds and my Y estimate was 1.52 seconds. And they're relatively quite similar, which makes sense as total path oscillates with X and Y components, and a 0.08 second difference between these two vector coordinates are relatively small for the scope of this experiment.